This is the Earth Science Classroom. You are logged into the Earth's interior now. Different videos in the series, and this video I'm looking at the Mesosphere Part 2, the lower mantle. In the first video, we looked at the composition and different characteristics, and looked at the pressure and the temperature and the density and the different changes or phase changes that happen within this mesosphere area, and how it's a pretty very large, component of the Earth's interior. So, and yet it's obviously deep enough where we are still having very educated guesses on what really happens there, and there's still a lot of things to discover. However, there's one thing we look at in particular with obviously all layers, and especially with mesosphere, going from the transition zone from 410 kilometers to 660 in the asthenosphere, branching down into the mesosphere, the lower mantle, and then get down to this kind of like 200-kilometer kind of depth where there's another, basically these red lines are discontinuities. All right, so here as well, discontinuity. And that means there is a change in the velocity of the seismic waves by earthquakes observed by scientists as they go through the Earth's interior. And the different speeds of the waves indicate what kind of medium or material that they are passing through. And the speed of the wave, distance, and the amount of refraction can indicate the changes and really creates the divisions within the Earth's interior. Much like the change in temperature and the inversions kind of let us know the boundaries of the Earth's atmosphere and the layers there. So it's a similar thing, just with seismic waves rather than temperature. We do have a temperature geotherm going through the Earth's interior, but that is not really as big of a marker as the seismic waves. So seismic waves. Now, in previous videos, we discussed in detail the transition zone and how there is a slight increase in the velocity of the seismic waves. And then let's do this. The seismic waves come down like this, certain speed, then increase a little bit, and there's fluctuations within this zone. And then it hits the mesosphere at about 660 kilometers. And the velocity is around 11 kilometers every second. And then what's going to happen is that's still a very fast seismic wave, and that's based on the density and composition. It's going to increase. It's going to increase even further as it goes down deeper through the mesosphere, down to an average of around 13.5 kilometers per second. So it does increase with depth. And at 13.5, it is way the most fastest portion or depth at which the seismic waves get to. Now, this is in terms of the P wave. Now, the S wave is considerably slower. I'm going to draw the S wave. The S wave would be like this, where it comes into the TZ and hits around 6 kilometers per second. And then there's a slight increase with depth to around 7 kilometers per second. Again, these are generalized averages. They can be faster or slower, depends on where they are on the Earth and the composition, density, temperature, and pressure. But the average is around 7. So it hits and this is the Core-Mantle boundary, which is a big deal in terms of a very important discontinuity found by a guy named Gutenberg, German scientist by the name of Gutenberg. And this is in 1914. Oops, 4 there. 1914. So a few years after Mohorovich found the crust-mantle boundary. So Gutenberg observed that obviously there is a different speed between the primary wave and secondary or shear wave. And let's take the primary first. So what he found was at the Core-Mantle boundary at this depth, he found that this blue dashed line that shows the velocity of the primary wave, the P wave, actually goes back about 40% So it reduces its velocity, so it gets slower by over 40%, and then continues into the outer core at about 8 kilometers per second. And then what happens with the secondary wave, the shear wave, the S wave, is pretty awesome. It doesn't actually continue. It actually gets stopped. This S wave actually hits this depth of 100 at the Core-Mantle boundary, and where the P wave slows down and continues at a much slower rate or velocity, the S wave actually gets stopped. It gets stopped, it gets diminished, diminished so much that the S wave no longer continues into the outer core. Now, the outer core we know is liquid based on mass of the Earth calculations, density, composition of iron and nickel, and the mass calculations. They pretty much know the outer core, and also with experiments done on the surface, we have also replicated that the S wave will not go through a liquid. And I'll get onto that in the outer core video, but for now, obviously, just realize at the bottom of the mesosphere, the core-mantle boundary, the S wave is stopped, doesn't go any further, but there is articles suggesting that there is a much less evident P wave or second P wave that is formed from the diminished S wave. Again, some articles have mentioned that. That would be something to look at further in college, maybe college geophysics, but for the high school level, it isn't really required. So the P wave and S wave going through mesosphere, the reduction in the velocity of the P wave at the Gutenberg discontinuity, and what you're looking at is Gutenberg using this information to figure out the composition of the outer core, the state of matter, obviously being liquid, and he figured out that there is a what's called a P shadow zone created. So if you excuse my very basic drawing, we have the earthquake, this X marks the spot, this focus right here, the earthquake, and the blue is the P waves, the green is the S waves. The blue is going to move faster generally than the S wave, and what happens is you have this one right here, this line right here, which has this sudden wave propagation, has no real interaction with the outer core. It just goes through the upper mantle crust and then obviously through the mesosphere and comes out, and let's say obviously it comes out about 105 degrees, okay, from the earthquake. And then what happens is this other P wave comes through as a different trajectory, different angle, and it actually interacts right here with the core-mantle boundary. It reduces its speed from 13.5 kilometers per second down to 8, and it is refracted, very severely refracted. And that's going to obviously continue at around 8 kilometers per second, and it's going to again get bent and curved and come out here. Okay, so normally it would come out here, and it'll just be a regular thing. But because the outer core is liquid and there's a change in the P wave velocity, let's erase that a second. What you have is this refracted bend to the P wave wave going through the outer core that comes out here at 140 degrees. So what you have is what Gutenberg discovered and experienced was that on the other side of the planet, there would be a 35-degree width or range whereby there would be no experience or no P waves at this part of the planet. So he called it a shadow zone, as in you're the shadow of a tree and the sun is obviously diminished, or you're in the shade. So you're in the shade of basically the outer core, and it's creating this area on the surface where they cannot feel any P waves. So they wouldn't feel the earthquake shaking. But here, house here, or a house here, they would feel the earthquake shaking because it's not in this 35-degree shadow zone. Okay, and so it also would happen over here as well. There'll be two shadow zones, the way it basically works. So the outer core was established as liquid, and the core-mantle boundary was a very important discovery in understanding our Earth's interior as a whole. And the effects on the surface were evident. And also, the S wave, again, is stopped right here, okay? But also, if you're looking at, there will be some deflection of that wave, okay? And be deflections of these P waves and S waves going forward through the Earth. But shadow zone was very important, and this was by Gutenberg in 1914. So this led to a lot more investigations into the core-mantle boundary at about 2,900 kilometers below the surface. Now going back to the original diagram, I have here a D layer, which is just around the core-mantle boundary, and it is a thin layer, maybe only 100 kilometers thick or 150 thick, and it was seen on the seismic charts of the velocities of the P wave and the S wave. Is it's regional, it's an area of regional discontinuity disk. So in various areas of the Earth, you'd have a slowing or speeding up of the waves, but it wasn't consistent around the entire world. And also they realized that the material, the composition must be heterogeneous compared to the rest of the Mesosphere, which would probably be homogeneous in terms of the olivine, pyroxene, and pyrrhotite phase changes. But this could be caused by, some articles mention, the descending slab and breakup of cold slab rock coming down from subduction zones. All right, guys. So hopefully we understand the mesosphere a little bit better in terms of the velocity of the seismic waves, the transition zone at the top, the D layer down at the bottom, and obviously the core-mantle boundary, which is a big, very distinct change for the velocity of the waves and the discovery of the P wave shadow zone. All right. Thanks for listening to Earth Science Classroom. Hope to see you soon.